Thanks. Thanks for the invitation first. I'm Xiaotong, she's Qingyi. We're both PhD students at MIT studying transportation. We participate into this Amazon Last Mile Challenge. We won the first place. Second place, sorry. That's why we're inviting. Yeah, the first place are sitting there. All right, nice to meet you guys. Yeah, probably a student-based team, right? A little bit background about us. Like, none of us are working closely with the VRP. So Qingyi works on machine learning image generation in transportation field. My own research, I do like robust optimization, large-scale optimization to solve the urban transportation problems. I work a little bit on the VRP, but on the school bus routing problems, not very close to the all those meta heuristics. But it's a great workshop. I've learned a lot. There are many interesting topics. So I'll start my presentation. It's not. Oh yeah. Okay. It will be two parts today. First, I will talk about our solution for the Amazon Last Mile Challenge, and then Qingyi will talk about a little bit on the extension work we did after the computation to get better results from our initial efforts trying to use the machine learning to solve that problem. But the final solution is all about the TSP, so it's all OR-based solutions. The research team, besides me and Qingyi, they're also Dr. Bai Chunmo, who is also a PhD student at MIT who recently graduated, and he's currently a research scientist at Lyft. So about this Amazon Last Mile Challenge, it held like March to June 2021. The target of this challenge is you have a set of routes, the real routes taken by the drivers, and you want to develop an algorithm to predict the routes that driver actually taken. So this is a very tiny example showing the computation. So you might think that the black dashed dots is the shortest path, but the driver might take the actual routes that does not make sense to you, right? And you want to create a model that predict this actual route. And our solution won the second place. Also, additional information is the data we have and provided into this challenge. We have the route information. We know the exact date. We know the depot or distribution center. We know the departure time. We know the vehicle capacity. We know the observed sequence, which actually taken by the drivers. And we know the service quality about that routes. There are three categories, whether it's a good quality routes, medium quality, or low quality. And it's defined by Amazon. And we have stop information, all the stops you need to visit, right? The packages you delivered at each stop. Yeah, and also we have package information. You have the size of the package, time window, planned service time, whether you successfully deliver that package or not. So those are all the information we have. And we also, another question is how do you know whether the routes you generated is good or not? So Amazon also defined a disparity score, which defined here. Basically, the lower the score, the better your routes is similar or close to the actual routes taken by the drivers. So I won't go into the details, but the key point is this similarity score is non-differentiable, meaning that if you're developing any machine learning algorithms, you cannot directly use this as your loss function. So that's one thing to keep in mind. Yes. So what is our final solution? So we develop a hierarchical approach. So basically, the key message is we split the TSP problem into a zone level and a stop level. So zones are also defined by the Amazon. And we first do a TSP at the zone level, and then within each zone, we do a stop level TSP. So that it has several benefits. First, for a given route, we find that there are at most 47 zones, but there can be more than 200 stops. So you can directly use any exact solvers to solve a TSP with 47 instances, right? That's pretty easy. So you don't need to worry about the heuristics. The second thing is we found that from the actual routes taken by the drivers, they actually traverse all the stops in a zone first and then move to the next zone. So it's a direct observation from the data. And also getting the zone sequence right is crucial. If you got the zone sequence right, it's high likely you got a great score. Yeah, and the benchmark we are trying to compete when we're developing our algorithm is just the naive TSP problem. So it gives a score about 0.054, and it's already a very good score. So why TSP performs such great? We have several observations. First is the drivers does not take routes randomly. So they have a route suggested or provided by the app zone, and they tend to follow the routes. And those routes are generated by a very complicated version of the TSP solver within the app zone. So even you use the simplest TSP, you still got a pretty close results to the actual routes provided. And also we found that drivers do not deviate too much from the routes provided. So that's why the TSP is good. And our solution is to improve the routes get by the TSP. So how do we improve that? Because we are trying to predict the routes taken by the drivers. And if you think about the TSP, it basically, you consider the travel times, and you find the path with the lowest travel times. That's a root cost. And on the other side, you have the actual routes taken by the drivers. If you still think about this cost matrix, it has a pretty high root cost for that actual route. But for each driver, he or she might has his own like customized cost matrix. And he's taking a shortest path based on his own customized cost matrix. So the idea is if we can find all the paths between the TSP and the actual routes taken by the drivers, so all the routes that have a cost smaller than that, in between, and we modify the distance matrix such that when we do another TSP, this route will come. Then that's the ideal scenario. Then we have a modified algorithm for our algorithm, and then we can solve that. So that's the ideal approach. And in the end, of course, there are just too many paths between those two paths. So we cannot enumerate all of them. So in the end, we look into some heuristics to find that. So those are very simple heuristics. First, the driver can complete the orders within one zone and move to the next one. Second is we actually found that when driver moved from one zone to the other, it actually follows a rule called difference of one zone. So for instance, there's a zone ID provided by Amazon, the larger zone like A-2. The smaller zone within the larger zone is 2A. So typically if a driver complete order from A-2 point to A, it has high probability to move to A-2 to B. And if it's from 2A to B, then it's a difference of one zone. That's a simple observation we have. And also, driver tends to finish the larger zone first, like the A-2 first, and then move to the A-3. And also, we found that drivers either goes to 10 geographically nearest location to start or 10 geographically furthest zone to start. And those are all the heuristic we used to modify the distance matrix. And after we modify the distance matrix, we solve the TSP. And we do a final post-processing is to reverse the first stop by the drivers who take the routes. And finally, our solution improved the score for the naive TSP from 0.05 to 0.375. So that's all the approach we take to win the second place. You might think it's a very easy approach. That is because 95% of our effort are used to explore the machine learning-based method. And we failed. None of them beat the naive TSP. So 3 days before the deadline, we turned to the TSP-based method. We developed that very simple heuristic, and we got the second place. And this is the challenge objective of the Amazon Last Mile Challenge is you have to use, or they encourage to use all the AI-based, machine learning-based method But our experience is none of them work, or we do not find the right way to implement them. Some method we tried, like we tried end-to-end learning, we tried pointer networks, we also tried reinforcement learning, but none of them beat the TSP. So I'll let Qingyi to talk more about the machine learning-based method.
So I'll be talking about the journey we embarked on and struggled with deep learning-based methods. And two types of end-to-end deep learning-based methods. One is the simplest linear architecture, where we have a very myopic view, where we predict the next stop based on the previous one. And the more popular one, which is pointer networks, and what we talked about in this workshop as well, is the encoder-decoder architecture, where we encode all the stop information before we start decoding, so we have the global view. And so these are all the machine learning-based methods we tried during the competition. So we did a benchmark 0.054 here, and then the sequential neural networks, and then sequential neural networks trained with RL, because that non-differentiable disparity score can be trained by RL, but there's 6,000, it's not enough, and RL doesn't really converge very well in our own experience. And we also tried pointer networks. And one thing to note here is that all of these perform very similar or slightly worse than naive TSP. That's because it's given a naive TSP solution as a warm start. So it should perform similarly to TSP after all. And none of them beat the naive TSP method, so we submitted the rule-based TSP solution. And after the fact, we got to reflect. And deep learning are known for its capability to encode complex patterns. So it should at least encode the information and learn the information that we by ourselves hard-coded into those TSP. So after that thought, we made a few observations on why the learning was not successful. First of all is deep learning models require large amounts of data. And the pointer networks, which received a lot of success in the follow-up works, they use 1 million. And we have 6,000 as a training set. And also the algorithms are very sensitive to the input sequence order, the encoder-decoder architecture. And we see that although it's not desired, but we gotta encode the stops in some sequence. Although we have a global view at the end, the encoder outputs do have a sequence to them, and the encoder output are encoding only up to what we saw before. So they are very sensitive. And first stop prediction casts a large influence on the final score. I think this is because of the scores. Because if we make an error on the first stop prediction, the error kind of cascades and there's no recovering from there, because it's a similarity between the sequences. And lastly, the models are trained by standard cross-entropy loss. And cross-entropy loss just measures whether you make a correct prediction at one certain position. It doesn't really take into account of the relationship between the stops. So if you shift by 1, then by cross-entropy, you're all wrong. But by disparity score, you're pretty accurate. So that's the discrepancy between the training scheme and also the evaluation scheme. After the facts, we thought that some of these we can remedy, but some of these we just can't do anything about it. And so we wondered, can we make it work? So we did some more work and devised a pairwise attention mechanism added to the pointer networks, so that our proposed pairwise attention-based pointer network can achieve somewhat similar score compared to what we did in the challenge. Note that the score is different from the previously quoted 0.054. This is because this is a follow-up work and it's evaluated on the complete test set released by Amazon, but the 0.054 was the sample test set during the challenge. And I'll explain more about what we did after the fact. So this is the architectural diagram of our pairwise attention-based pointer neural networks. And I'll explain this architecture from three components. And one is the backbone of it, and then how we added our custom attention. So should be all pretty familiar with the backbone of the encoder-decoder architecture. It optimizes for the conditional probability of observing a sequence, and that's the backbone of our approach. And the pointer networks added in attention. Attention is used to select a member of the point sequence at each decoder step. So basically, at each decoder step, we have a decoder output vector, and we compare it against all of the encoder output vectors for all of the unvisited stops. And we decide which one is more likely to be the next choice. So in this case, we kind of have a global view of comparing what we're currently at with all the unvisited stops. So the decoder output is relayed from the start. So we have the global view of all the stops as well as the already decoded ones. And then the encoder output stops are used to reference the unvisited stops and to choose one. However, the problem with this is that we're missing some local knowledge. So the current attention only looks at the previously visited stops and the encoder output vector of the unvisited stops. So there's no explicit representation of, say, the travel time matrix, which is crucial in our TSP formulation. And also, like, there's no way, we haven't really encoded the zone-based rules that we have discovered during our TSP exploration. So we wonder, is there any way to actually encode those local information? And we devised this pairwise attention algorithm. Simply, it is just to calculate the pairwise attention between the last decoded stop, and then calculate the travel times, and also say the zone-based information, and concatenate it with the embeddings, so that we have a more comprehensive local and global view when we calculate attention. And this ASNN stands for Alternative Specific Neural Networks. And it is one special neural network inspired by discrete choice models in economics. And the idea of it is that we usually in neural networks, simplest, we have all the input on the one side and then passing it through a neural network and getting our output. So it computes the utility value, or we call it the feature of alternatives by using attributes of all the input numbers. Why is this? So the alternative specific idea is that we have some parallel information. So in discrete choice, it's all the choices. And then in our case, it's all the stops. So we do have, say, travel time between stops. They're parallel. So it doesn't really make sense that we put all the stop information on all at once, but rather we can separate them to make the network a little bit smaller, and also to take out all the unnecessary interaction terms so that it's easier for the network to learn. So in this case, it's a kind of a parallel idea where we separate the calculation into different blocks, and then the blocks all of these blocks for each stop do share the same parameters, so that it really makes the network a lot easier to learn. So the model training part, that's something we wasn't able to do. We're still using cross-entropy loss because we just haven't figured out a way to simplify the disparity score. And we didn't have a large enough data set to try policy gradient and reinforcement learning. Some post-processing. Theoretically, in these probability likelihood-based approaches, the alpha sequence should be the one with the largest probability. However, during inference, that's what requires to enumerate all possibility, because a greedy algorithm only gives you a greedy solution, and it could be that the highest probability sequence has very low probability to start with, but very high probability as we decode. So in practice, people just use greedy or beam search. In this study, we have the observation that first stop choice is important, and that there are discrepancies between highly probable sequences and highly scored sequences. So what we did is that we just generated sequences using the greedy algorithm. We didn't bother with like a beam search, and we selected the one with the lowest operational cost. Yeah, so So this is the performance table that I showed before with more information. And we added the prediction accuracy. We see that we, first of all, improved. So this is the alternative specific utility, and this is the normal attention we calculated. And we see that despite in addition to having improved scores, the prediction accuracy of the first 4 stops increased significantly by around like 10 to 15%. Also, I mentioned that there is another thing, which is the robustness to input sequences. And we added this red columns comparing to with TSP sequence as a warm start or just inputting random sequences. And we show that our pairwise attention-based algorithm can actually be a lot more robust to different input sequences. This is because at each decoding step, we can actually get explicit information on the travel times and the zone ID information and all other information comparing to all the unvisited stops. So this makes the network a lot easier to learn, so we don't rely on the latent codes, and the algorithm needs to learn where the stops all are by just encoding and passing the LSTM along. This paper, we wrote up a paper about it, and it was just accepted in Transportation Research Party. So yeah, let's be honest here. Our machine learning-based approach is still worse than the first place solution. It still achieves a higher score. It only performs on par to our second place solution. And yeah, we got to more thinking on why, because we think that we did everything we could to improve this algorithm. There may be more to do on search and stuff, but we did what we could. We identified 4 areas that still can be improved in the future. First is the problem setup. As we mentioned before, drivers follow the path provided by Amazon, but it's not available to us. So if we want to learn the driver behavior, so having the planned or the navigation routes would be really helpful here. And another is sample size. The 6,000 routes are spread in Los Angeles, Chicago, and Boston. So the information was pretty sparse, to be honest. And yeah, so if we have a larger sample size, the learning would be a lot better. And data availability. So the feature provided us, we have a lot of features, but we experiment with them, but they're not very useful. So we had number of packages, package dimensions. Planned service time are empty, I think, for the most part, and delivery windows are sometimes 6 to 8 hours. So we weren't able to use those information very efficiently. And also, when deviations such as backtracking exists, reasons for failed delivery were not presented to us. So we don't really know when the driver is going to come back. So if there's no people answering, or there's just congestion and the driver decided to deviate and deliver to some area else first, or there's an accident or whatever. So if we have that information, the learning would be a lot more efficient and effective. Lastly is evaluation criteria, and we mentioned this a lot of times already. So we think that the disparity score is a very good way to evaluate the differences between 2 sequences. But if we can work out a differentiable version of it, it could be a lot better, but we just weren't able to. We did try. Just to conclude this presentation, we just want to summarize our experience working with optimization-based algorithms and deep learning-based algorithms, specifically end-to-end algorithms. Optimization has the strength of there's no training required, and it's stable and deterministic, and it offers a global view, so it's shortest path and whatever cost matrix that you identify. But it is less flexible, so you can only modify the cost matrix for the most part. And it has the curse of dimensionality. It can only solve the zonal sequences, but not the stop level sequences. And it relies on hard-coded knowledge. So all of these, we have to go into the data ourselves and mine out all the zone ID patterns that we mined out. On the other hand, deep learning approaches are capable of integrating multiple data sources. We can even integrate more if we want to. It's fast route generation, so at application time, it takes pretty much no time. But it requires a very large sample. And it's intensive during training, and it really relies heavily on input feature quality. So if you have very good input features, then machine learning can work well. But then if you don't have useful features, then it doesn't learn at all. Yeah, so that concludes our presentation. Thank you for your attention.
Thank you for questions.
Yeah, it's a comment. So it's true that within a zone, drivers follow the path or traffic signal, but the first stop visited depends on the last stop visited in the previous zone. Did you guys use that kind of?
Yeah, we have a small heuristic to do that. So basically, we consider between 2 zones, compare the distance between any 2 pair of stops, find the 9 nearest pairs, and use that as the end of the last zone and stop at this zone, and calculate and minimize the travel time, and use that to decide which is the first stop and last stop within each zone.
Yeah, because the way it's done is using dynamic programming, starting from the end.
Yeah, that
But you guys
probably
have
too
that
complicated.
process.
Yeah, yeah. We use very simple method to address that. Yeah.
So, thank you very much.